In this video, we're going to look at how to use Taylor series and Taylor polynomials to do approximations and to represent functions. So we're going to start by looking at a Taylor series centered at 0. This is also called the Maclaurin series. This is the formula for a Taylor series centered at 0. Each term has the function or one of its derivatives evaluated at 0, then divided by n factorial. So, for example, the x squared term is going to have a coefficient, and the way you would calculate that coefficient is the second derivative, evaluate that at 0, then divide by 2 factorial. So you can do that for all of the terms, and you can build the Taylor series. In practice, that might be difficult if you had a complicated function. Taking multiple derivatives gets more and more complicated. So we'll look at a very important but nice example, the exponential function. The exponential function, whenever you take its derivative, you just get e to the x back. And when you plug e to the x, when you plug 0 into e to the x, you always get 1. So the function evaluated at 0 will be 1. All of these derivatives evaluated at 0 will be 1. So we just end up with the following expression where we have x over 1 factorial, and the x squared over 2 factorial, plus x cubed over 3 factorial, etc. This power series on the right is exactly equal to e to the x. Now, it's going to be useful to be able to approximate functions using just part of the Taylor series and not the whole thing. That idea is related to Taylor polynomials. So here we start with the graph of e to the x, the exact function. Then we're going to start approximating it using Taylor polynomials. A Taylor polynomial basically takes your Taylor series, but only keeps a couple of the first terms. In particular, a Taylor polynomial of degree n only keeps terms until you reach x to the power n. So for example, t1, the Taylor polynomial of degree 1, stops after x to the power 1. So in this particular case, it would be 1 plus x. That provides an approximation to the graph of e to the x. In fact, this would be called a linear approximation, which you may have seen in Math 140. This red curve, this red line, approximates the blue curve, and it does so very well if we're very close to 0. But as we get further away, the approximation becomes less accurate. If we increase the degree of our Taylor polynomial, say to second degree Taylor polynomial, now I'm including the x squared over 2 term as well, this curve is closer to the e to the x curve than the t1 polynomial was. And if I include even one more term, look at the Taylor polynomial of degree 3, that will also include x cubed over 6. Now the Taylor polynomial and e to the x are almost right on top of each other. So it's a very good approximation over the plotted region. We're going to find the Taylor series for e to the negative x cubed at x equals 0. And we're going to approximate the function at x equals 0.5 using the first 3 terms. One way you could do this is by using our definition of the Taylor series, calculating a bunch of derivatives. However, it's actually going to be simpler to use our existing expansion for e to the x. And when we want to look at e to the negative x cubed, all we need to do is replace every single x that appears in this formula with negative x cubed. So this x turned into negative x cubed. This one turned into negative x cubed. It gets squared, etc. We can simplify this. For example, the quantity negative x cubed raised to the power 2. You need to remember to distribute this power of 2 to both hit this 3, turn it into a 6, but it also hits this negative 1, and negative 1 squared is 1. So now the coefficient of this term is positive. However, the coefficient of this term is going to be negative due to this negative. The coefficient of the x and 9 ends up negative because we have, that comes from doing this term, which is x cubed, but that cubed hits that negative 1, and negative 1 cubed is negative 1. Point is, we end up with an alternating series where each term has a power of x that's increasing by 3. So this is the full Taylor series, but we're going to approximate it using a Taylor polynomial that only includes the first 3 terms. So that will be up to the x to the 6th term in this case. So this would be called a Taylor polynomial of degree 6 because it includes up to x to the power 6. So I'm replacing the x's with 0.5 because that's the value I want to approximate the function at. And if you plug this quantity into your calculator, you end up with about 0.8828. Whenever you make an approximation, you also want to have some idea what the error is in that approximation. And when you have an alternating series, you can approximate the error by calculating the absolute value of the next term in the series that you didn't include. So like we included these first 3 terms, we did not include the 4th term, so I'm going to calculate the value of the 4th term at x equals 0.5. Plugging in 0.5, using a calculator, we get 3.3 times 10 to the negative 4. So this value that we found is accurate within this amount. Just to wrap up, I mentioned that the Taylor series can be applied at any value of x, not just x equals 0. So if you make a Taylor series expansion at a, one difference is that all those zeros turned into a's. Another difference is that instead of just having x and x squared and x cubed, you have x minus a squared, x minus a cubed, etc. Having a Taylor series centered at a is useful when you want to approximate the function at values of x that are close to the value of a. And last, if you have an alternating series and you approximate it with a Taylor polynomial, as we saw in our last example, the error is going to be less than the absolute value of the drop term with the lowest power of x. So if you included these first 3 terms, you would calculate this last term, and it gives you a maximum value for the error.